what is PyTorch? PyTorch is a library that stores data in arrays, if you want, multi-dimensional arrays, so it's very much like NumPy.
Hello everyone, myself Neeraj Lunawat. I welcome you to AI India community. This is going to be our very first training session. Today we have Thomas Viehman. Those who don't know about Thomas has a written book called Deep Learning with a PyTorch, and also he is distinguished member of PyTorch community. Thomas is a core PyTorch contributor, so it's good to learn from contributor himself. I requested Thomas to start training session from the scratch. Only prerequisites are going to be here, Python basics. Okay, without any further ado, let's start with the training session. Over to you, Thomas.
Hi, I'm Thomas again, and to go along with our little conversation, Neeraj asked me to also write a little tutorial about PyTorch. And so the condition was that I should start from scratch. And this is quite a challenge because there really is so much to talk about. And you probably heard in between that actually with two of friends, I wrote a book on it, Deep Learning for PyTorch. And we're basically going to follow along that structure, except that I will try to not use anything without mentioning a bit about what we're doing. But obviously this will be a lot shorter than an entire book to not strain your patience. And also you will forgive me that I make some advertisement, and so here's my website, and there you find my blog, hopefully with interesting posts. And every once in a while I also advertise a course that I'm doing on there. Okay, so but now let's start from scratch. Here's a literally empty Jupyter notebook, and we'll start having some fun. And what we're going to do is we're going to train a neural net, or at least part of a neural net. We will see about that to classify plant diseases, and specifically tomato diseases. So first thing here, this is supposed to be about PyTorch. So what we're going to do is we're going to import some things, and I'll import Torch, and I'll also import Torch Vision, which is the library dealing with images and videos from the PyTorch team. And I'm also going to import, without a lot of saying why, I'm going to import Torch utils data, because we're going to talk about data. And then I'll import, and I should spell that correctly, I'll import the library Tim, and this is Ross Whiteman. It's PyTorch imaging models, and so this is TIM, and the last M, I don't know. Maybe it's here from the imaging and then models they say. Okay, and you need these three libraries. If you haven't installed them already, you go to pytorch.org, and then you see here with Get Started, it will have instructions how to install PyTorch for various versions of CUDA or Rockham. And also Torch Vision. And Tim, you just have to install yourself with Conra up here. Okay, so let's do this. And now, what is PyTorch? PyTorch is a library that stores data in arrays, if you want. Multi-dimensional arrays, so it's very much like NumPy, and you can see this like if we accept that PyTorch calls these arrays tensors, so you can do torch.tensor and then have something 1, 2, 3, 5, 6, 7, and no, I did something wrong. Right, I should make this a list of lists, and then I can view this as a 2-dimensional array, and similarly I could do 3 or more dimensions. So one thing to know here is that in contrast to these lists, these arrays are also always homogeneous in that all these things have the same data type. So if I include one float here, PyTorch will notice that there's floats we're talking about, and will make all of them float. We can also see this here. There's a D type, a data type, and so the standard PyTorch data type is torch float 32, 32-bit floating point, single precision. If I remove this, I can, and I have all the integers. The standard integer type is 64-bit integers, which may or may not be a good choice, but yeah, I'll leave it as this. Okay, so what can we do with tensors? One thing is we can index them just like NumPy arrays. So I can do starting from the column row number 1. No, this doesn't make sense. I'm taking the first row and starting from the second column. I have this 6, 7 here. This is something I can do. I can also do torch tanh of t, and I get the tanh of it. Or I can also write this as t.tanh, which gives the same result, of course. I can multiply things, divide them, do operations on them. Okay, so we have this multi-dimensional array thing. Of course, these things always have to be hyperrectangles, so I can't have things that are of different length. This will now work with PyTorch. Okay, so here's tensors, but obviously we don't want to type in whatever data we have, but we want to deal with data, right? With real data. And so the first thing we're going to do is we're going to get some data set. It might be something you collected yourself, but for this tutorial we'll use data here that I got from a website called Mendeley, and it's data for this paper, Identification of Plant Leaf Diseases using a 9-layer deep convolutional network. And so it's a data set from an organization called Plant Village. And if you search for Plant Village dataset, you'll find a link at Kaggle, at TensorFlow, also quite a bit of links on GitHub. Okay, so this is what we're going to use, and specifically we'll use the Plant Leaf Diseases dataset without augmentation, and you can download it here. I have downloaded it already, and so I'll briefly drop into the terminal here, and here we have the data set, and so yeah, I downloaded the full thing, probably not with it. Just download the zip file, and if you unzip the plant leaf diseases without augmentation, you will find that it has a number of directories for various fruit, and so it's apple, cherry, some background without leaves, healthy plants, like here's tomatoes. Tomato has a lot of plant diseases here, and it has healthy tomatoes, and then it has tomatoes with various diseases. And in each of these subdirectories, there's a number of images, and then these images will be images of leaves that are healthy or have a given disease. Okay, so when we have data, the first thing to wonder about is how are we going to represent this data. And in fact, after we learn what tensors are in our book, we talk about how to represent data. And so images, obviously, we're all used to digital images from screens and phones and stuff. And a big part of what we paid for the phone or for computer screen, is the resolution that it can do. So we are all familiar with the concept of representing images as RGB values for each pixel, and this is exactly what we do for the images. And so Torch Vision has this functionality. We can use Torch Vision .io.read image, and read an image from the data set, and I put this here in Plant Village. Now we go to healthy tomatoes. I will just pick any file name here, and these are pretty long path. Okay, so this is as close to the original image as possible if you want, and I can save that to a tensor, and we already see here that D type is uint8, which is kind of a common format to have images in values 0 to 255, and we can also see the shape is in this data set is 256 times 256, which is a very useful base data type. We see that the channels are here in front. This is different between various libraries you might use. In PyTorch, it's typically you have a batch dimension if you have one. We don't have one here, and then the channels, and then the height and the width. For other things, for example, it's common to have the channels at the end of the shape. This is just how you organize it in memory. So Torch Vision also has utilities where you can show this, but I want to use a transform that is called toPillImage, and this will allow us to just see the image. Here it is. Okay. It's not overly spectacular, but so we might use a different class, tomato with bacterial spots, that looks different. Maybe not that different, but yeah, we'll see what the computer makes out of it. Okay, so these are the images. One of the, and really you should look at images more when you have a data set. Look at your data as hand as you can. It's really important. But so if we have this, the next thing here is, and this should really be one of the first things, is we have these folders with images in them. But once we trained our model, how do we know how good it is? And what we're going to do in this kind of business is that we will set some data aside and use that for evaluation of our result. And then we will not use it to train our network. And so this is called a holdout set. And we're even going to have two holdout sets, one a validation and one a test set. This is kind of the common practice because you will have to make certain decisions and you have one holdout set, the validation set, that you can, or sometimes it's called the development set, where you can make decisions about the neural network architecture, how long to train it, with what learning rate, etc. that you can use the validation for. And then the test set is what gives you the final quality, and ideally you would not look at it until the very end. Okay, so how are we going to do this? We need a few more Python modules. So glob is a module that can like give us a list of files from a mask, and then we need the OS module and also SHUtil. I will see what they're good for in a minute. Okay, so I promised to do this from very beginning, so you have to put up with me doing this fairly slowly because I'm not that fast here. So I will take here all my directories. And these are and I use glob.glob, and this will give me the directories. At least I thought, yeah. No. Okay, if I use that for a glob mask. Oh, okay, it's cat ears, not this. Okay, so these are the directories, and obviously I should sort this in order to have like a reproducible result. I will sort these by the alphabet. Even if that means that healthy is the last category, one might have thought it's the first, but okay, never mind. And so we have to create our data set, and we will loop over the categories, and then we will get the files in each category. So we have again the sorted files that start with the directory name and then the mask is any file, and then we can print the maybe I call this the cat name. Print the number of images, and so we have this is the smallest category with 373 items, and the others have at least around 1,000 examples. And so what we're going to do is we're going to set aside 10%. So for the two holdout sets, so we have holdout size, and I will not care too much, but so the pedantic person will round up the holdout set size, and so this should be rounded up 10%. And so train images will be train image names will be the image file names up to 2 times twice the holdout size to the end, and then we have val im fns, and this is im fns from this on to the holdout size, and test im fns is the remainder. And here you can see, and this should be minus holdout size, and here we can see how the slicing notation in Python is very handy. Okay, so we can see that, yeah, I should, yeah, so we want integer division here. And so these are the holdout set sizes, and this looks about right. And so when you have more complex data sets, you might have additional constraints. For example, if you have medical data, you don't want images from the same patient to show up in the training and the validation set, because it might spoil. And so there's quite some data specific things. What you should have is that the holdout sets are independent, stochastically independent, if you want, of the main of the training data set. Okay, so we'll do with this split. Now, the best thing is to really set this in stone, this split, so nothing bad can happen. And what I'm going to do for that is I'll just create a directory, and I'll do this for I'll call this data, and then we'll use path drawing to be clean. And I'll call it, make it a local directory called data. Oh, I didn't want that. Okay, data, and then and then train, and the category name, and it's okay if it already exists. Okay, and I will do the same with and hopefully, yeah, this doesn't exist right now, right? And so I will also make a validation and a test directory. And this is how, for example, ImageNet, as one of the most famous datasets, is also organized. There you have train, val, and test, the splits, they're sometimes called, and then for each category you have a directory where the images live. So now we have to use shell util.copy, and for fn in train image fns, we are going to copy it to the training directory. So yeah, I never know if I should make this a name. Train D and then oops, I have val and test, and now I have to make absolutely sure that I'm not screwing this up. Okay, so we can, for D and offense in the pairs train D, train image offense, and val D, val image offense, and test D. And this is not very interesting, but realistically you also spend a lot of time with these not so glorious things in any given project. Okay, so we make the directory even if it exists, and then we have to make so we make this directory, and this includes the category name, of course. This was what had me wondering for a moment here. And so we can say copy the fn to the directory. And this will work because I can supply a directory name here, which is very neat. Okay, so let's see if that runs. It runs, and it takes some time, which is good, I guess. But just to be sure, we're going to check out if that worked. Okay, so we have test, train, val, and so these yeah, this seems like an awful lot. And so what happened? I would expect, oh yeah, this was of course wrong. I should have used fns here, and now this is all broken. I better remove it. So I said I'd better make absolutely sure, and now it's a bit quicker too. And so it's a good thing that we checked on this. And now, we see that it has about 1800 images in validation and test set, and it should have about 8 times as many in the train set, right? And this is 8 times 18, that's about 14 and a half. That's pretty good. Okay, so we have our train test split, and we could now go and read our images with the data, but we want to organize it a bit better. And so PyTorch has these things that are called data sets. And if we look at Torch utils dataset, Torch utils dataset, this will be I should only use one. So okay, so it's an abstract class implementing a dataset, and basically you need to have 2 things. All subclasses should override getItem, supporting fetching a data sample for a given key, and method len that it gives the length. So I could now do the following. Then I write a dataset class myDS, and it's derived from Torch utils dataset, and I will need an init function, and I will pass either data train, data val, data test to it, and then I will have to check the cat names and get all the images from that. Okay, so I will keep this up there with me, and then I need to get all the images, and if we look, they're all with capitalized .jpg. But I might as well get all files in these directories. Of course, it's safer to do it differently. But yeah. So all our files are in the top there, but we want to have all categories and all files in all categories. So these are the files we have, and to make my life simple, I will keep the categories here, and this will be ospath base name, ospath the name of a given file name, and of course I only need each one, so I construct a set. This will eliminate the duplicates, and then I sort it. And so I can initialize this with data train. And I should call this method init. It's not, it's pronounced without the 2 underscores, and I can see here that I have my categories, but I also want to be able to get the category of a given file, so I will make this I make a mapping from category to the number, the numerical, the position in this list, and I'll do this for IC and enumerate self-done categories. Okay, so I have this mapping, and now I needed a len method, and this should give me this should give me the length of the data set, and so this is easy. I just return the length of self.files, right? And now I have another method that I need to implement as get item. Here cell, I have to take an index and then return the ith element, so the file name will be self.files idx, and then the category, just cat, will be self, and I will return the numerical index. The category is ticked at ospath base name, ospath the name of the file name, just like what I had up there, and this will give me a numerical index between 0 and 10, because I have 0 and 9, because I have 10 categories, right? Oh, I can, yeah. Okay, and then I just can read the image. Torch vision IO read image fn, and then I just return a tuple, and this will be the image and the category. And so if I do this and then I do len ds, this is just the number of files that we saw, and then I can do ds0, and this will give me an error. List object not callable. Oh, okay. I need to take this index here. Sorry about that. Okay, so I have the image, I have the output, and now one thing that's particular about our data set here is that I return the image as a uint8, and the reason I'm mentioning it is because usually if you're not doing a PyTorch tutorial, you won't be doing this dataset from scratch, but you might use a pre-made PyTorch Torch Vision dataset that achieves pretty much the same thing. So I can do ds2 Torch Vision dot datasets, and then there's an image folder dataset. There's also pre-made datasets for some things, from imnes to stl to ImageNet. But this image folder dataset basically also takes a root directory, data train, and then I can see that it's if I take the length, it will be the same length, obviously, same files, and it will do pretty much the same thing. I'm not sure whether it will, yeah, it won't have the same ordering of the images, but so it returns a pill image, which, yeah, it's this pill image, and this was, I can transform this back to a pill image, right, with Torch Vision transforms functional and to pill image. Okay, and I should just pass the tensor, and you see it's a different one. So this has different, potentially also different category names. Okay, class to IDX. You see it sorts the classes too, so it will have the same classes, but the files will be in a different order. And also it returns these pill images, which is a bit different from the integer tensors that we get from our dataset. Typically, you would then have something like here the transform, and the transform in our case would be Torch Vision transform. And now, because I want this as a class, I will use not to pill image, but the reverse to tensor. And now if I look at DS0, I will see that it's a tensor, but if I look at this more closely, I find, and you see that now it's a different thing that has index 0, apparently. And now, now I can look at the D type, and this is float 32. So this will give me an image that has range 0 to 1. If I look at the minimum and the maximum, yeah. So this doesn't have bright white on the image, but it could reach up to 1, which is different to our case where we had 0 to 255. If we want to make this more standard, we could just divide by 255 here, but I will not do that. I will do it in the training loop instead, because then I can do it on the GPU, which will be faster. Okay, so we have a data set, and I'll just, you can remember this image folder if you want, but I'll just go with our own data set. Okay, so here's the train data set, but which is great, right? We have a data set, awesome. But what we're going to do is we're going to want to batch things. And so now the cool thing is that this batching, like getting data and arranging it, is a bit of a tedious thing. And it's very similar for all data sets. And this is why, or for many data sets, and this is why PyTorch offers a data loader here. And it has, it takes a data set, and we can give it a batch size. And we can just say, give me 64 images at once. And I can say if I want them shuffled. And I will say shuffle true, so it shuffles the images for each training run. There's a bit of a debate whether that's needed or not. I can say I want more than one worker. I will not do this right now. But so there's another thing. I don't want a tiny last batch, so I'll just say drop last batch. And this means that if there's only less than 64 images left in my that haven't been processed yet, it will just ignore the rest. And often we see that when we use batch norm or something like this, this or something that gathers statistics, this last batch will be really weird. We won't use batch norm today, so maybe it's not needed, but I'll use it. Okay, so if I sample from the data loader, next iter train DL, I see that it's a list of two things, and the first thing is a rather largest tensor, and then it's a smallish tensor, and so these are all our images, the U and 8 tensor, so I can also show the shape. So the batch size is 64 as we requested, 3 channels, 256 times 256, and the other tensor is the categories, and it has one number, so it's a one-dimensional tensor, shape 64. Okay, awesome. What are we going to do with it? Yeah, we're going to train a neural network, but we're not going to train the neural network from scratch. But we'll fine-tune an existing network. That is, we take a network, typically these are pre-trained on ImageNet, and we're going to adjust it to our needs. And so one thing we will do here is we'll write a little training loop. Or first we get the first we get the model, and this is, remember, what we used Tim here for. Could have also used a ResNet, but I'm going to use a transformer because I'm so hip here. And so I take this model, and it's going to be from Tim models, and I'll use the diet base patch 16 to 24 transformers pre-trained equals true. And so Ross does a really great job and assembles all these models and weights. And so here's a transformer in all its beauty, 12 blocks, just like we want. And it has this head, and the head makes it into 1000 ImageNet categories. And so if we were to run it on our data, it will probably say leave all the time. And we can try that, but let's talk about something else first. And I've already shown you that we're going to get integer tensors 0 to 0 to 255 out of our network, but that's not what the transformer expects. So as you might imagine from this, we want to resize our images to 224 times 224. But there's also a thing that we need to normalize our data. And so what happens is that in ImageNet, data is normalized to zero mean standard variance. And so we have to do the same thing to get reasonable results. And I will cheat here, and I have written a blog post that talks about this a bit. And so I can never remember the mean and standard deviation. But so what happens is if you have ImageNet as 0 to 1 floats, it will have this mean and standard deviation. And so the normalization transforms it to something. Sorry. It transforms it to a more meaningful number for these models. It's not clear that it would be needed these days. With batch norm or layer norm, we could probably do without this standardization. But now we have it, and we'll just follow along normalize data like this. So we let's just get a batch here, and I'll do it this manual way. Next iter. Usually you do it in a for loop. You can just say for image comma lab in train DL, and then it will loop. But here we'll grab 1, and now we can do this. And this is the next, and I forgot this when I talked about tensors. The cool thing about PyTorch relative to NumPy, or one of them, is that you can move tensors to the GPU, and you do this by saying image to CUDA, or maybe if you want to have it extra fancy, you say device equals torch.device CUDA, and then you say image to device, and this will move it to CUDA, and then we can also say lab equals lab.to device. And then we want to normalize things, and now we can do images divided by 225, and this will give us 0 to 1, and then we want torch vision dot transforms dot functional and transform this 0 to 1, and we could make it in one step. There are the right parameters to do this in one step, but I'm not going to figure it out right now. And it says CUDA launch blocking because it's out of memory. And now I will pause the video and I will check what's running on my graphics card and stop some stuff. I'll be right back. Okay, so here we're back, and I'll restart the notebook, and I run all this again. I wouldn't have needed to run the sorting again, right? And so this should be normalized, and now it works. And if you see this, now I have the minimum will be something like minus 1 or 2 typically, the maximum plus 1 or 2. The standard deviation is not quite 1, but okay. And the mean is closer to 0. Okay, so if I run this through the model, I will okay, I need to get the model too. And now it says the input size doesn't match the expected image size. So I'll take care of that too by using touch vision, transforms functional resize, and I will just, or I can do okay, so I will use torch vision, and this is in a way the more common way to use this, is to use these classes. And so I will use random resized crop, and so my target size is 224 times 224, and now I use image is crop images, and you can usually you see this path as a transform to the dataset, but by moving these bits to the GPU, we're going to be much faster, and so this is a good thing, right? And now I didn't move this to the device. Okay, now we're getting something, and if we look at these predictions, there was an awful lot of them, and now I'm out of memory again. Can you believe it? And the reason is that I'm recording graphs here a lot, so you can PyTorch will keep track of your computation in order to allow you to take the gradient and see how to change the parameters. And you can tell PyTorch not to do that by saying with torch.nograd, and then it will be much easier on the memory, but once you're there, it's a bit hard to recover, so I'll just restart the notebook here, and I will redo these steps, and now we're safe, and we have these predictions, and now you can see that these are rather large, and this is 64 and 1000 classes, and these predictions, technically they're called logits. So if I do predictions.softmax -1, and this is the dimension, I get a vector of 64 prediction probability distributions, so this sums to 1. And I can take the value with the maximum probability, and you see that yeah, this is most of them is 936 or 988, and this will be something about plants, hopefully. So I will just lazily copy paste this code here to find out what these numbers mean. So if we do this, we import JSON, and so ImageNet classes 988 is acorn, so not quite, but and head cabbage, also not quite, but yeah, something with plants probably. So we need a model that makes more reasonable predictions here, right? And so what we're going to do, if we look at this model, this had this map to 1000 ImageNet classes here, and we're going to replace this last layer, and we can have a little alternative to this with torch.nograd, and that is we can say for p in model.parameters we turn off that the parameter requires gradients, and then we're going to add a new linear layer as they had, and so model.head, and we do this by just assigning a new linear layer here, torch and then linear, and we need to have the same number of features, and we have 10 outputs. And what does this do? We can look at the forward method. So when you use a model, it will always go through the forward method by default, if you call it. And so what linear does is it keeps a weight parameter and a bias parameter, and it will just call a function linear. And so this is a linear layer in the neural network, also called a dense or fully connected layer. Okay, so this linear is just a call to a linear layer. A linear layer is a matrix multiplication essentially, and then it also holds parameters. And usually we would need to take care about initializing these properly, because PyTorch doesn't always do a great job of this, but so no, we don't have to. Okay, so we can do predictions again, and I forgot to send this to the device. And now all the layers that had been in the model before, they will not need gradients, but these last ones will. And so if I look at the predictions, now they require a gradient again, and this lets me train a model, and this we will do by iterating over our data loader for ims labels in train DL, and I will just take this here, and we move things to the device, then we apply this cropping. We might also augment images here, so we might do a random rotation, something like this, but I'll skip it for now. So we take predictions, then we take the loss, and this will be the cross entropy loss. It's the loss that takes logits. Always think about what kind of inputs your model needs, right? We had to normalize the images in order for them to be good to feed into the model, and also think about what kind of things what kind of inputs the loss takes, and this takes logits as the input. So raw unnormalized scores for each class. This is exactly what the model gives us, so we have good luck here. So we can just say this is predictions, and then our labels are just in the right format for this loss too. And now we would need an optimizer if we want to optimize something. So we start an optimizer here, and obviously here's a riddle. What learning rate should we use? I will use the Adam optimizer, and I can just pass in model head parameters, because these are the only ones I'll optimize. And I will just use 3e minus 4 as the learning rate. And I will this is just something you can do. You can also use something different. This is the hyperparameter, if you want, that you're most likely going to experiment with. And also there's more sophisticated things you can do here, like learning rate schedules. You really should look into this next, but we won't right now. Okay, so if I have this optimizer, I can say here, after I have the loss, I will do opt.0grad to clear everything that's there from the last round. And then I will say last.backward, and this will start the back propagation. So the parameters in model.head get gradients of the loss, and then I'll take an optimizer step, and that's it. And every now and then, if and I should really maybe at the end I will print the loss, and I will make this definition of the optimizer separate, and now I can run this. At least I thought. Boolean value of tensor of more than one cross entropy loss, and this should be the functional loss too, just like I like to use the functional things, and other people have different tastes about this. So this takes a while, actually. Maybe I should have done something to display progress and also display loss in between. We can look at how it uses the GPU. One thing we see, it only uses 3.5 gigabytes of the GPU memory, even though there's quite a bit taken here. This looks funny. Maybe I need to restart the computer pretty soon. But so if we want some intermediate output too, I can just use enumerate here, and then every 100, if I percent 100 is 0, I can print, and I don't need any of the information, so I will just print the loss.item, and then I can see every now and then it'll tell me whether the loss has gone down. And so while it's running, the GPU utilization will be 100 typically, which is pretty good, because it means that our GPU isn't sitting there waiting for data to arrive. What we also see is that the loss isn't decreasing all that much. So we might have to play with the parameters a bit. So let's reinitialize the model and see what the loss is at the start. So it starts at 2.37, and we might wonder whether it's going down enough or not, and I will tell you a trick. So Andre Karpathy on his blog, and the problem that I have is that I always spell it wrong, and so he has a blog post from 2019, a recipe for training neural networks, and this is really great advice. You should read like every line of it. And so one of the things is one of the things he recommends is to overfit a random batch first, or a single batch first, in order to make sure that everything's set up quite right. And so if we want to do this here, that's easy, because now that we have trained it, or we can do it like what we did here. We have this, right? We can grab one of these, and then we just have to make these like a different variable, and now it will only work on one batch, and we should see the loss decreasing very reliably. And so let's see what happens here. It goes down and down. Oh, maybe it doesn't go down. Oh no, it took a second batch, right? That's not how I imagined it to be. And there's another bug I'm having here, and that is that I'm redoing this normalization all the time again, which is kind of not so good. So we'll do it a little bit different. We'll just sample here 1imp0 lab0, and then I will, instead of using the image labs that I have from the data loader, I will use that. And this should work more reliably. And we see, and now this was from not much, but we see this this overfits things easily, right? And so this part of our setup seems to work, and it can also go below 0.24. Okay, so and now typically you don't just like run this for one round over the data, but you typically make many of them, and so you have a loop over epochs. And oh, before we do the loop over epochs, we might talk about validation a bit. So if we want to evaluate how our model is doing so far, and now I should retrain the model, say for one epoch, without this using the same image all over again. So if we want to know how well our model does, we need to do a validation loop. So we can do basically enumerate val dl, and now we can do the same thing. In particular, we will do the same augmentation, except that we will use a center crop, and from torch vision transforms functional center crop. And this needs an image and target size 224 224. Okay, and then we will use with torch.nogra, because we don't need gradients in the validation. Predictions is model images, and now we just want to. We could also ask for the loss. Let's just do that. It will be instructive. But we also want to have the accuracy, and so the accuracy will be predictions, and you saw that I could use argmax, and now I want to know how many of them are equal to the label. And here's a little trick. I will make this a float, and so I will, in order to not just have this for one batch, I will use total loss and total accuracy. And what I'm going to do is I'll start with 0.0 and loss 0.0, and I should do this outside the loop over the images. And now I will just say accuracy is accuracy plus the current contribution, and I also need to take keep track of the total number of images our model has seen. I could take this from the dataset or the data loader, but I will just say here nval, and here I will use plus equal because it will remain an integer, but here it will be a tensor after the first round, and I don't really want to use plus equal when it changes the type of the variable. It just makes me feel not so good. So this is the batch size, and so I know how many things I have seen here, but then I should use here maybe instead of reduction mean, I should use reduction sum, and then at the end, and note that I will keep this on the GPU, and this is to avoid synchronization points. So I will here say print loss, or maybe I will do loss equals loss divided by nval, and accuracy is accuracy divided by nval, and so I can just take the dot item here because it's outside this loop, and now I can say print loss equal and accuracy equal, and this is validation, right? Because I used the validation data loader here, except that the data loader wasn't defined. Yeah, my fault really. So the validation dataset obviously runs on the validation data of the split. And here I have val dl, and here I have val ds. I replaced the wrong part. And obviously I don't need to shuffle it, and without gradients I can easily take a little larger batch size. And now I can see how it goes. And here's a problem, and the reason is here I need to sum to a scalar, and so the accuracy is 30%, which is not so good. And here I have the wrong thing. Good that we that we fell for this. Maybe the training was all screwed up. Yeah, this looks much better now. Probably something wrong with the training loop that I didn't catch. Then maybe we better start training from scratch. Okay, so it's the last starting at 2.3, and now let's see if this goes down. And it's 1.13. Okay, and after the first epoch, I have yeah, now the accuracy is looking much better. And we see after only a few epochs we have really great accuracy, and let's see if we can push it like above 90. Yeah, so you see that I'm only needing a few epochs here to really get somewhere, right? Okay, so here we're above 90% accuracy, and obviously for more serious use you would do a loop here and have this much better, and then you could decide when to stop based on when the validation accuracy stops increasing, or the loss stops dropping, and then at the very end you could evaluate the accuracy on the test set, which would work just the same. So obviously, if you want to know more about like not from scratch thing about training in neural network with PyTorch, one great way to learn something is look at this book. We also discussed it, and obviously more detailed content and courses are on my website, which I have to make some advertisement here. Here we could train for a few epochs yet, but this would make the video much longer, and so I hope you enjoyed this, and I hope you will do great things with PyTorch. Thank you for listening.
You have covered a lot many things out there. Thank you so much for giving a hands-on session on PyTorch. Guys, if you have any doubts or any queries, feel free to comment. Also, if you want more such a training session in the upcoming time, please let us know in the comment section. Thank you so much for watching this one.